everyone. So we have our next speaker, the last speaker of the session, Lucero Hernandez-Cedillo from the University of the Basque Country, with the title of the talk, Optimized Tilted Fiber Bragg Rating Sensors for Calcium Detection with Fast, Green, and Highly Sensitivity. So please.
Thank you so much. Hello, I'm Lucero, thank you. And I'm doing the second year of PhD in the Basque Country. My advisor, Joel Villatoro, and we collaborate with the BC Materials with Unai Sullivan. Okay. We are in the engineering faculty, so they say, hey, we have this problem and we need to solve it. So the problem which they give us was calcium detection. Why? It's important by biomedicine, water monitoring, industry, and the challenge for us is, okay, not exactly for me, but for all the team, it's do organ on a chip, and they want to do a heart. But my mission is detect all the factors. I start with calcium. In the future, I need to also check glucose, CO2, and pH. Okay, the challenge, we need to put all these sensors inside. So for that, need to be small, sensitive, rapid, and eco-friendly, because we'll be work in contact with cells, so we don't want to kill them. Okay, so why we choose TFBG? Because they have a lot of information. Thank you for Elena and Jan. They explain us a lot of it, so I could be briefly. We have the light, we have a tilted grating in the fiber. So we have two kinds of signals. The modes, which are guided modes, and the cladding modes, which are in the surface. So with these structures, we could have better reaction to index variation. And also, if we do some treatment inside, we could detect other kind of effects like scattering or ionic interactions. So advantage, it's label-free, it's compact, and we could, in the future, do a multiplexable devices. Okay, the methods which we use was prove how much we could improve the signal. So we have the clean version. For this, probably it's not 19, sorry. Probably 0, because you only need to clean it. And then with this, we want to see the index refraction variation. But we used two other cases. One was put in the surface. First we clean, then we put plasmon to activate the surface, then uptest by 30 minutes, and then 1 hour in gold nanoparticles of 40 nanometers. Okay, that is the one. But it's important to say we are not playing with the plasmon resonance here, because our signal is independent to the plasmonic signal, so we are using polarization. It's only like without polarization. Okay, and the other case is put uptest, but instead to put gold nanoparticles is add peroxide hydrogen, and with this we remove the, I don't know if you are familiar with uptest, has a nitrogen, and then you could have hydroxyls, but we remove everything. We only maintain the carbon in the structure, and so all the structure will conserve only a carbon, plus the peroxide hydrogen, we could obtain carboxyls. And we are comparing this with this, and also with clean. Okay, important to know. So we have our different signals. The clean is in black, with carboxyl is in blue, and with nanoparticles is in red. We are focused in this region, where is the cutoff region. And we also are taking account different reactions, because for the first, we don't have nothing. It's the clean fiber. And in the second, we are not consider the polarization. So we are only seeing the scattering of nanoparticles. And in the last, we have an interaction, ionic interaction, because the carboxyls interact with calcium. Our system is like this. We have a sensor interrogator, then we have the fiber, and in this side, we put a mirror or reflector. Okay. Then, so for the analysis, we go directly to the cutoff region, which is around, I could say, here. And for all the sensors, we searching for the same region. We obtain the cutoff. How we know there is a cutoff? Because if you see, there is a tendency, and then this peaks, if you try to group with the envelope or something like this, it's different. So our cutoff is this. And we study the modes by changing the calcium concentration to how much? The less concentration was 1 micromolar, and the biggest was 100 millimolar. And for all, we tried this concentration and observed these cutoffs. In some cases, if you want to, if you could think the cutoff, it's moving to the left or right. And we also study the slope of each peak. How much sensible is this signal when you add calcium? The thing is when you have a bigger concentration, the signal go up. It's less intense. So you could define each concentration by the specific signal of the same sensor. Finally, and go for a copy fee, our results. When our fiber is clean, we obtain almost 1 millimolar, okay, 10 less. Then we have nanoparticles and then carboxyl. So with carboxyl, we obtain around 5 micromolar, and we decrease considerably the limit of detection. And also we are trying to put in a basic reaction the carboxyl. So with that, we want to manage to go to 1 micromolar of calcium. So in conclusion, our sensors achieve 2 micromolar level calcium, which is a good average for the experiments in organ on a chip, are fast, like 90 minutes. I think it's okay because some are doing 1 day or 2, low cost. And also our method don't use anything which is bad for environment, so our friendly protocol. We are want to then using the potential of real world, for example, doing experiments for devices or this kind of stuff. Thank you.
Thank you very much for your talk. We have time for some questions from the audience. Anyone? Well, I have to go. Yes.
Thank you so much. That was very lovely. Why do you use the gold nanoparticle for scattering? Your interaction is finally with the COOH ions, right? So what is the role of having the gold nanoparticle scatter at all?
Yeah, in the beginning, we wanted to only to know if only with the index, with the change of the index, we are available to check it. That's true, but was not enough because it's not specific. So then when you have a unique interaction, it's specific, not only check for index refraction, but we need to improve this because also you could, with this, by a ionic interaction, you could detect cadmium or sodium, so could be do a problem with your measurement. In this moment, we are only in clean samples, so we know but are we checking? But in the future, we need to do specific for another ions.
Thank you. I also had the same question. And any other question? Yeah, I'm going to ask, maybe we have some minutes. One last, what are the next steps apart from selectivity? Just the integration with another sensor, same technology, other type of sensors? Or what
Yeah,
are-
in this moment, we want to multiplexing. We also have another kind of sensor as interferometric sensors with hydrogels. So if we are able to mix them in one only interrogator, could be super small to check it, because in this moment the sizes of each of these commercial sensor is around 1 centimeter, and we are talking about less than 1 millimeter. So it's the way.
Thank you very much. So if we have any other question, if not, let's thanks the speaker again. So that's the end of the session. Now